Hello, everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Rula Deeb. I'm a Senior Principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of SERDP and ESTCP by Dr. Kurt Preston, followed by a list of upcoming webinars in the series. After Kurt's opening remarks, we will transition to the technical portion of the webinar. Today's event features two Department of Defense projects related to conservation efforts in desert environments. First, Dr. David Lytle from Oregon State University will talk about predicting, measuring, and monitoring aquatic invertebrate biodiversity on dryland military bases, a very important topic given that aquatic habitats are among the most imperiled habitats in these areas. His presentation will be followed by a brief Q&A session. Next, Dr. Christopher Castro from the University of Arizona will discuss more extreme monsoon precipitation in the southwestern United States and the potential implications for DoD facilities. His presentation will also be followed by a second Q&A session. We will conclude the webinar with an interactive Q&A session with both Dr. Lytle and Dr. Castro. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions well in advance of the Q&A sessions. On the slide, we have provided a few suggestions in case you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. With that, I would like to introduce Dr. Kurt Preston, who is the Program Manager for Resource Conservation and Resiliency for SERDP and ESTCP. Dr. Preston's career has tracked between both civilian, university, and military positions. As the Associate Vice Chancellor for Research at the University of Nebraska-Lincoln, Dr. Preston led faculty development efforts to improve research competitiveness and also worked with technology transfer personnel, academic departments, and colleges to build university research capabilities. Dr. Preston has served as a member of Chief of the Army Corps of Engineers Environmental Advisory Board. Kurt, I'd like to turn it over to you now.
Thank you, Rula. I'm happy to welcome everyone to today's SERDP and ESTCP webinar. SERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the Department of Defense, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP and other research programs that are designated to transition technologies out of the lab and into the field. Especially important on all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts that are conducted. There are 4 program areas in SERDP and 5 in ESTCP. The Energy and Water program area is only found in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapon Systems and Platforms, are SERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focused on research demonstrations that were conducted under the Resource Conservation and Resiliency program areas. Areas of investments including understanding DoD relevant ecological systems, assessing the impact of military training on marine mammals, managing threatened, endangered, and at-risk species and invasive species, understanding watershed processes and management, developing the models and tools necessary to understand infrastructure vulnerabilities to and the impacts from climate change, and understanding the impacts to air quality from DoD activities. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see, upcoming webinars will cover a broad range of topics, including laser depaint and surface preparation mechanisms and technologies, platforms for underwater and nearshore munition surveys and building envelope technologies. And the next Resource Conservation webinar is on December 7th. And this webinar will focus on the management of novel Hawaiian ecosystems and will feature 2 speakers, Dr. Susan Cordell from the USDA Forest Service and Dr. Rebecca Ostertag from the University of Hawaii at Hilo. You can find more information about upcoming webinars at this link. Registration is now live for webinars through to the end of the year, and I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. In addition, we would appreciate it if you would take a moment to complete the survey that will pop up on your screen at the end of this webcast. I am pleased to announce that for the first time since 2011, the SERDP ESTCP Symposium will be held next November in Washington, D.C. The 3-day event will showcase the latest technologies excuse me, that enhance the DoD mission through improved environmental and energy platforms. I hope you enjoyed the webinar today.
Thank you, Kurt. And it is now my pleasure to introduce Dr. Dave Lytle, who is a professor in the Department of Integrative Biology at Oregon State University. Dr. Lytle's research uses evolutionary ecology to understand how organisms and communities are shaped by disturbances such as floods, droughts, and dams. Dr. Lytle earned a PhD from Cornell University and conducted postdoctoral research at the University of Chicago and the University of Arizona as a Smith Conservation Fellow. Dave?
Great. Thank you, Rula, for that introduction, and thank you, Kurt, for introducing SERDP. Good to be here. So my project is looking at predicting, measuring, and monitoring aquatic invertebrate diversity, but I think a lot of the ideas here are going to be generalizable to any freshwater ecosystem and organisms that are associated with that. So I want to sort of address that broadly. In terms of the agenda, I'm first going to lay out the importance of a very dynamic hydrology for understanding dryland streams, especially in arid land regions and desert regions. I'm going to talk about an aquatic invertebrate data set that we have put together and developed for southwestern military lands, at least a select number of bases. Then I'm going to talk about some niche and neutral modeling techniques that we have developed for generally estimating biodiversity and also something called functional diversity that I will explain and discuss. And then cap it off by talking about some web-based tools for managing this biodiversity on military lands that we've developed. Okay. The motivation. So, why are we studying dryland streams? Well, I would like to flip that on its head and say we should all be studying dryland streams because they are the general type of stream ecosystem that we see on the landscape, especially here in the western United States. You can see from this map where the percentage of intermittent streams, so these are channel forms that only flow very occasionally during the year during rainfall events typically, is the norm for places like Arizona, New Mexico, Southern California, Nevada. And essentially our question is, given that, military bases in the southwestern U.S. harbor a lot of these intermittent streams, but also pieces of perennial stream. And how do these stream networks, taken together, maintain biological and functional diversity? That's our general research question here. To understand that question about stream networks, we have to understand that stream hydrology is extraordinarily dynamic, especially in dryland ecosystems. If you look at those pictures off to the right of the slide there, that's Brown Canyon in the Huachuca Mountains of Arizona, on Fort Huachuca or near it. And a stream bed that was completely dry on one day could be hit by one of the sudden monsoon rainfall events that Dr. Chris Castro will be talking about in the second half of the presentation and become activated. So that dry stream bed suddenly becomes an active stream channel and in fact can contribute in particular ways to the biodiversity of the aquatic ecosystems on that military base. But this stream drawing, it occurs at different spatial and temporal scales. And essentially, what's going to happen is the prevalence of dryland rivers changes depending on land use. Humans need water, climates change, and all of these things are going to affect the location and the abundance of these intermittent streams. And one of the things in particular is that when streams dry, when they go from a wet phase to a dry phase, they change the longitudinal connectivity of aquatic organisms. So they connect up perennial reaches and then disconnect them in very characteristic ways. Okay, next. Well, one thing that we know is that this is our future. Streams will become more intermittent and more fragmented spatially into the future under almost any climate model and almost any prediction scenario. The graphs that I'm showing you here show stream networks on Fort Huachuca in Arizona. And on the right of the screen, these are the upstream portions of different streams. Okay, each bar in there is essentially a stream. And I'm sorry, each bar in there represents a different time of the year. And you can see that on the upper panel that the typical thing is the upstream reaches high up in the mountains are perennial. So that's the dark blue. As you move downstream, you get into a lot more red there. That's essentially, oops, wait, am I looking at this backwards? Yep, I'm looking at that backwards. So upstream to downstream is essentially, the thing to focus on there is that the white areas show no areas of no flow. So you can see that during certain times of the year, June and July, there's a lot of white in the upper panel, and that indicates that there's essentially a dry period, and that's a typical seasonal thing in Arizona streams. Under projected futures, though, that dry period, the white area, becomes greatly expanded. Starting April through July, we expect longer periods of no flow, and in general, just less flow longitudinally going from upstream to downstream. Okay, so that's our future, and this is based on a gauge network of flow sensors that detect flow in actual streams coupled with climate models from another SERDP project. So these are real data. Okay, well, how does this matter? So what that previous slide shows is that we can expect more spatial variability, we can expect more temporal variability in stream flow. We abbreviate this as SV, spatiotemporal variability. Well, on the one hand, some of that is good. Ecological theory tells us that if you have variability across a landscape, that can increase niche partitioning and lead to higher biodiversity and diversification on ecological timescales. But that also gives us measurement challenges. When there's high spatiotemporal variability, the detection probability for a species will decline. And the graph on the lower right shows us a schematic of this. So on the x-axis, we have spatiotemporal structure of a network, so going from low to high. On the y-axis, we have sampling effort. And on the z-axis, the vertical axis, we have the probability of detection. And you can see that if you have low spatiotemporal structure, in other words, a lot of homogeneity across the landscape, it's easy to detect species. They're out there, you know where to look for them, they're there all times of the year. But as you add that variability, depending on the structure, species can be harder to detect and in fact require really high degrees of sampling effort in order to reliably find. So for something like invertebrates, which are diverse across the landscape, that can be problematic from a management point of view. Move on here. So you can think of detecting species as a two-part process. So first of all, it might seem pretty obvious, but species have to be physically present at the time of sampling. Okay? Well, that sounds maybe a little too obvious, but in fact, a lot of species are not always present in the places you want to sample them at all times during the year. They may be in a diapause stage and not available for sampling or detection. They may migrate from one microhabitat to another. Birds are an obvious example of this, because they have seasonal migrations. And so, that ecological part needs consideration. And layered on top of that, species, given that they're there, we must be able to observe them or detect them in some particular way. And that schematic that you see below there is just a diagram of a Bayesian occupancy model that incorporates both of these factors. So it has an ecological component and it has a detection component. And essentially, those parameters just give us the probabilities of detecting a species conditional on that species actually occurring in a habitat. And we can make these models as simple or as complex as we want. They can account for seasonality. They can account for different types of microhabitats, such as intermittent streams versus perennial streams, and so on and so forth. So it essentially allows us to blend together factors about the ecology of the different species along with their detection probabilities. And when you do this, you get a sense of what kind of effort you need to expend in order to reliably detect the full diversity of any given species on the landscape, not just aquatic invertebrates. But in any case, we chose aquatic invertebrates as our test case for a variety of reasons. Number one, you go to any aquatic habitat, even in the most arid regions you can find, you're going to find some aquatic invertebrates there. Second of all, invertebrates span a huge range of diversity, of life history types, of ecological roles that they play in aquatic ecosystems. We focus specifically on the OCH fauna, so this includes the odonata, the dragonflies and damselflies, Coleoptera, which includes the aquatic beetles, and the Hemiptera, or the true bugs, the aquatic true bugs. And we looked at these at 3 bases: Fort Huachuca in Arizona, White Sands Missile Range, New Mexico, and NAS China Lake in Southern California. And in addition to fully characterizing the invertebrate fauna across a network of streams, we looked at a lot of physical data and also did some estimates of sampling effort, power, and efficiency, just to understand the full amount of effort it takes to understand the full aquatic community. Okay. Moving on here. So in the Huachuca Mountains of Arizona, so this is a map of southern Arizona, and you can see that it's a whole archipelago of Sky Island mountain ranges. And the Huachuca Mountains are one of those mountain ranges. And if you focus in, there's a fair amount of topography there, and that contains this network of intermittent and perennial streams that we're interested in. And these streams are on active military ranges where there are different types of activities going on with vehicles and with personnel, and so it's a working environment. But these working environments also contain an extraordinary amount of biodiversity hidden away in these desert habitats. Here's some images of perennial sections of streams. Those perennial sections of streams are typically in the upland sections, and they flow down into intermittent sections like this one that harbor a different kind of biodiversity. And so again, we're looking at the connection of both of those in the stream network context and how that maintains biodiversity. So we sampled all 3 bases, and we found a lot of biodiversity there. We looked at 1/3 of a million specimens, and just in terms of raw species diversity of OCH and also including some other taxa, Fort Huachuca came in at over 300 taxa. China Lake is a much more arid environment, and so it had a smaller species pool, but a different set of species. White Sands Missile Range somewhere in the middle. And essentially, in addition to using this to test models, this is a great baseline data set for future management efforts. So we have a good characterization of the biodiversity of the invertebrate fauna on these bases at this point. And so what did we do with all this? Well, we used this data set to look at niche versus neutral models and how they predict biodiversity. And just briefly, a niche-based model is a very mechanistic model. It's like that Bayesian occupancy model that I showed you earlier. And it essentially says, okay, species have a niche that interacts with the environment. It describes where they live. And essentially, we can use that to predict where else they might be on the landscape. Neutral models, and in particular neutral meta-community models, are fundamentally different. They require essentially no information about the biology of organisms, and they are essentially good at predicting overall biodiversity in the absence of a lot of information. And so essentially we use the neutral models as a null model for understanding the importance of other factors such as habitat degradation, invasive species, management decisions, and so on. Okay, so we're using both approaches because they really get at different things, different aspects of biodiversity. Well, just to give you some rough summaries, with the neutral models, we found that they perform really well or reasonably well in some situations and poorly in other situations. When flows were higher, so when we were looking at either wet periods of time with higher rainfall or at more perennial sites, the neutral meta-community models explained a good amount of the variability in biodiversity data. About 50% for alpha diversity and a little less than that for beta diversity, so looking across the landscape. Under dry conditions, these models, I think it's safe to say they failed. Essentially no predictive ability. So this was a new result, that the neutral models can tell us something about biodiversity, but only under wetter conditions. Furthermore, we discovered a novel thing about biodiversity estimate using the neutral models that had not been reported in the literature before. And essentially, many of the classic estimates of biodiversity, such as the Sorensen Index, different versions of it, and a few other biodiversity estimators, essentially will give you the wrong answer if you're comparing habitats that differ quite to a large degree in size. So in other words, if you're comparing small streams, large rivers, small ponds, bigger ponds, if there's variability in habitat capacity, those estimates will be biased and misleading. And the only one that is not is a newer estimate that was developed in the last couple of decades called the Chow-Sorensen Biodiversity Estimator. It's kind of a technical point why that occurs, and I would point you to some of our research papers on that. But this is going to affect how people measure biodiversity, not only on military bases, but in pretty much any ecological system. So that's a very general result. Looking at the niche-based models, the big result that we found is that hydrology really matters. If you can characterize a stream reach reasonably well based on its hydrology, in other words, if you have instrumentation that allows you to tell if it's perennial, if it dries up for a brief period of time, or if it's dry for most of the year and only gets rewatered during more extreme rainfall events, then you can actually predict quite a bit about the invertebrate fauna that's going to occur there. And so just to illustrate this, what I'm showing you on the right is called a non-metric multidimensional scaling plot. Forget about that, but keep in mind that each one of those points on the graph that's shown by a short 3 or 4 letter code is one particular site on the landscape. And in this particular case, all of those sites occur on, this happens to be Fort Huachuca in Arizona, but we got the same pattern for White Sands Missile Range and also for China Lake. The polygon on the right are the perennial sites. The polygon on the left are the intermittent sites. And so what an NMDS plot does is it takes all of the complex community data, the species diversity and the relative abundances, and it plots them somewhere on that ordination. In this case, just somewhere in that 2-dimensional space. And so points that are closer together are more similar to each other in terms of their aquatic invertebrate communities. And so you can just see that there's a really strong grouping there. Perennial sites grouped together, intermittent sites grouped together. So just having that piece of information tells you a lot. If you know you have an intermittent site, then you know something about the community. If it's perennial, you know something about the community. And the communities are different. So in other words, you need to manage for both types of stream ecosystem. Okay, moving on. Well, now I just said that these communities are different, that the species are different. However, there's sort of a caveat that comes along with that we have discovered. If you look at the functional or trait richness of the invertebrates, it tells you a little bit of a different story. So the plots on the previous slide showed you what the invertebrate communities look like. And so those are the different species of Odonata, Coleoptera, and Hemiptera and how they sort out in that ordination space. Well, what you can do is take each species and figure out what its functional traits are. Okay, so in other words, is it large-bodied? Is it a predator or is it a detritivore? Does it reproduce rapidly or does it reproduce slowly? So for every invertebrate species, there are lists of traits that tell how that species fits ecologically into the ecosystem. And so if you convert species into traits and then you do a similar type of analysis, you get some pretty interesting patterns. So the plot on the right shows a comparison of an Arizona stream, so a stream from Fort Huachuca, or a set of streams, sorry, with a set of ponds from Ontario, Canada. So completely different bioregion, completely different type of ecosystem. the only similarity is that both of those span a gradient going from intermittent to perennial. So intermittent sites are shown in, let's see, so we have ponds in the dots, streams are the triangles, perennial is open, intermittent is closed. And what you can see is that even though the species overlap of these habitats is almost zero, that on the left of the axis, intermittent ponds have the same functional trait richness and diversity as intermittent streams do, meaning they're ecologically, functionally very similar. And to me, this is pretty exciting, because what that means is that if you know something about the hydrology of your stream or your pond or your river or whatever it is, there is potential to manage, use some of the same management techniques across all of those really disparate ecoregions and ecosystems. Okay, so there's a real potential here for kind of cross-deployed management platforms for species management, at least in some cases. So that was a pretty exciting finding that we published just last year. Okay, well, in a little bit, I'm going to, I'll show you a list of publications that sort of get more into the nuts and bolts of all of these things. But one of the other things that we've deployed is a very much a beta version of a web-based graphical user interface just for visualizing biodiversity data. Because again, 1/3 of a million specimens spanning 3 different military bases on 3 different bioregions, many sites with different hydrologies across all of those. The data are almost impossible to organize and visualize without some sort of tool to do that. And so we've made a first cut at that. I've actually got a URL down there that should be live where you can play with this. And essentially, you can use the pull-down menus in the upper left to choose a season or a base or a particular site within a stream, and visualize different metrics of invertebrate diversity and biodiversity in the panels below. And again, this is just essentially serving the data that we collected as a part of this project, but the hope is that something like this could be used to catalog, inventory, store, and make accessible all of the biodiversity data that one could collect as part of managing these ecosystems. So there's just one particular view right there. I'm going to the next slide here. We're zooming in on Fort Huachuca in Arizona. I don't want to sound like we're biased towards Fort Huachuca. It's just that was the only base where we were allowed to take photographs. So I have a better photographic inventory of what was going on there versus White Sands and China Lake. But here you can see, you can look across different taxonomic groups, look at the raw diversity, both in bar graphs, pie graphs, whatever your preference is, and hone that in as fine scale as you want. Okay. So just to conclude, these are just the big picture conclusions here for management and conservation in particular. We need to consider the hydrology of sites in management plans. That's the big driver here. Hydrology is affecting biodiversity. It's affecting ecosystem process. It also affects how we design our sampling across the landscape. You need to incorporate the different types of hydrology into sampling designs. That's number one. Second of all, the functional diversity of sites, so not just the species diversity of sites, but the functional trait diversity of sites, can be similar across sites despite very different species pools. And again, there's potential here. We don't know what that potential is yet, but we need to tap that and look at some ways of doing cross-ecosystem management based on that fact. Third, we know that intermittent habitats, so these habitats that have been largely ignored by not just managers but biologists over time, these actually contribute to landscape level biodiversity. So it's maybe not the main contribution, but it's significant. And so we need to think about networks of sites rather than just focusing on that one beautiful perennial site that everyone's aware of, that we know has some important T&E species, but may only be just part of the story. And with that, again, here I'm going to skip over the publications, but little bit of further reading there. And I need to thank my project co-PIs on this, Julian Olden and Chot Munapirikal, and also all the base managers that made this possible. Couldn't have been done without that kind of support. And that's what I got. I think it's time for questions and answers at this point.
Great. Thank you so much, Dave. I would like to remind our audience to submit questions using the chat box on the left-hand portion of the screen. We have received a number of questions on your presentation, Dave. So the first question is as follows. Since organisms from intermittent habitats appear to have similar biological traits, how can the results of your work be used to manage ecosystems across multiple DoD installations?
Right. So can that trait similarity be leveraged to have sort of common management options? I think that the first and most obvious answer to that is that we need to consider those habitats and that they need to be part of a management plan. Rather than sort of ignore them because they do not reliably have water. So that's number one. And number two, I think, again, this is just sort of speculating on future sort of management options here, that managing for that hydrology could be a way forward. If we think in terms of just ensuring that a site has a characteristic hydrology that we can sort of monitor and maintain, a lot of the ecosystem function and then the species diversity that sort of goes along with that could follow. Now that might be oversimplification. I don't want to say all we need to look at on the landscape is the hydrology of a stream, but I think if you're going to put out any kind of monitoring network and look at one particular variant, that's very, very high on the list.
Great, thank you. And along the same lines with regards to leveraging information, can the biodiversity database that you talked about be applied to other DoD installations and other groups of species?
Right. So again, our database that I presented there is very much a beta version of a database. It shows what's possible, but it's not fully deployable and user-friendly. I mean, that's simply just the scope of the project that we're doing. But my feeling is that that kind of data management is the future, and that it's a worthy investment on the part of any organization, not just SERDP, that any organization that needs to monitor and keep track of biodiversity across the landscape, that you need a repository that takes the data in a very user-friendly way and then allows people to serve it out in ways that can answer their questions about management and about basic ecological questions. So the answer to that is absolutely yes. I mean, that type of database approach could be used for birds, for reptiles and amphibians, for plants. There's really no limit to it. It's just going to be a matter of programmers, working with programmers to develop the tools and the techniques to actually expand those databases so that they can incorporate those other groups.
Great, thank you. And one last question to you before we move on to Chris's presentation. Do you have any theories regarding why the neutral model you described tended to perform poorly during the dry season?
We have definitely speculated over that quite a bit, and in some of the technical papers we talk about it quite a bit more. And we think it has to do with species sorting or species filtering. So an intermittent habitat is a very extreme type of habitat in many ways. An organism that's an aquatic organism being able to deal with complete drought means that organism either has to have a way to go into diapause, or it has to have a viable way of dispersing to somewhere else in the stream network in order to survive that hydrologic filter. And so we think that that strong hydrologic filtering is selecting for certain species, and that filtering is essentially stronger than the neutral processes that a neutral model uses. Without going into it, a neutral model, it just posits a process of births and deaths and immigration, emigration, and diversification and extinction that essentially runs automatically and mathematically and doesn't really look at the particular species. But we think that the identity of the species is so important that it kind of overrides those typical neutral processes. And that's why the niche models work in that case, but the neutral models do not.
Great. Thank you so much, Dave, for a fascinating presentation. And with that, I just want to remind you that we'll get back and answer questions for you towards the end of the presentation. But right now, we're going to go ahead and turn this over to Chris Castro, who is an associate professor in the Department of Atmospheric Sciences at the University of Arizona. Dr. Castro's current research focuses on physical understanding and prediction of climate in North America through regional atmospheric modeling and analysis of observations. Chris is a member of the American Meteorological Society. Chris, please proceed.
Thank you very much, Rula, and thank you very much to Kurt for his introductory comments. I just have a minor correction to my affiliation. We have now merged with the Department of Hydrology at the University of Arizona, so we are now officially the Department of Hydrology and Atmospheric Sciences, and that merger actually took place during the course of the project. So my outline is I am looking at monsoon weather, and I will describe what the monsoon is here in Arizona in just a few moments, and some specific DoD concerns. And then we used an approach of convective permitting modeling to look at the changing meteorology of the monsoon. So I'll discuss the high-resolution modeling approach and its performance in relation to changes in the atmospheric environment and extreme weather, and then how we could translate some of this information to the actual DoD facility scale, and then finally some concluding points. So when we think about the North American monsoon or the Southwest monsoon in Arizona, we started out this project wanting to know, well, what is the effects of anthropogenic climate change on the monsoon? And there are a number of severe weather hazards which you see here relevant to Arizona and more broadly the Southwest, including dust storms, flash floods, microbursts, and lightning. So I'll play an example of an infamous dust storm event that occurred in the Phoenix metropolitan area. So this is specifically from July 5th, 2011. And this is a dust storm event as it is coming along I-10 towards the Phoenix metropolitan area. And I believe this video was taken in the Phoenix suburb of Ahwatukee, which is just south of Phoenix. There's just a massive wall of dust, and these things are kicked up by the outflow boundaries of severe monsoon thunderstorms. So the gust of the outflow picks up a wall of dust that can be over a mile high. So if you're interested we've included the YouTube link to the video, which can be accessed subsequent to this presentation. So some specific impacts of monsoon thunderstorms of interest to DoD include precipitation amount, precipitation intensity, and the wind gusts or outflow boundaries, and I've already shown you the illustration of how those can kick up severe dust storms, the spatial location of thunderstorms, and the timing during the day. Monsoon thunderstorms follow a specific diurnal timing. They tend to initiate on the mountains and then propagate off the mountains into the lowland regions more in the late afternoon to early evening hours. So we worked in conjunction with the 25th Operational Weather Squadron here at Davis-Monthan Air Force Base in Tucson, Arizona. And we started the conversation with them, well, what do they actually use for weather watch and warning criteria for terminal aerodrome forecaster tasks? And you see an illustration here from the actual task guidance used by the Weather Squadron, and I've highlighted a few things here. Damaging winds in excess of 50 knots, heavy rain greater than 2 inches in 12 hours, and if these are being issued as weather warnings, approximately 60 to 90 minutes lead time is required for these types of impacts. So the technical objectives of our project was to simulate extreme monsoon weather and evaluate their changes over time in both the historical period from the 1950s to the present, and then looking at climate change projections out to the next 20 years or so. And we employed a weather forecasting-based approach to the climate change projection problem. And here on the right, you see a figure of military bases in the continental United States in relation to the area that I occupy. And what is very unique about the Southwest, as you can see here, there's a lot of red area on the map. So we're dealing with a lot of spatially expansive military facilities. So some specific ones I will highlight in this presentation that are important in relation to the scientific conclusions are located in the southwestern part of Arizona, and those include the Yuma Proving Ground and the Berry Goldwater Range. So we used what is called a convective permitting modeling, and this type of atmospheric modeling employs a very high resolution grid spacing, nominally less than 4 kilometers. This is widely the paradigm used presently in weather forecasting. For example, by the National Weather Service, they employ a model called the High Resolution Rapid Refresh Model that is based on the Weather Research and Forecasting Model, which is what we used in this project. And we are increasingly employing this convective permitting modeling paradigm to climate timescale, so subseasonal to seasonal forecasting, out to climate change projection, and that the latter which was done in the context of this work. So when you see, well, what is the spatial scale at which these convective permitting models apply, on the right you see this is really the scale one must get to explicitly resolve cumulus convection, or in layman's terms, the individual thunderstorm scale structures like leading convective lines and outflow boundaries that I previously talked about. So when we think about monsoon thunderstorms in Arizona, they are forced by the diurnal mountain valley circulation. They form over the mountains during the late morning to early afternoon and reach a mature stage by about mid-afternoon. And this is just a photo of monsoon thunderstorms that take peak in their mature stage with gust fronts taken around 3 in the afternoon. If we talk about very strong, severe monsoon thunderstorms, these require specific atmospheric conditions, favorable thermodynamic conditions, so high atmospheric instability and sufficient atmospheric moisture, and dynamic forcing mechanisms of large-scale lifting and wind shear that helps the convection grow and organize. So here's an example of a monsoon severe weather event day, and this is just enhanced infrared imagery over the southwest United States and northwest Mexico. The specific date occurred in July of 2004. So you see the illustration indicates the various factors involved for a severe weather day for monsoon thunderstorms in Arizona. The presence of an upper level disturbance, which you see in the scroll of clouds, and these are called transient inverted troughs. So they travel from east to west along the southern side of a subtropical ridge of high pressure. There's low-level moisture surge, or the Gulf of California, or so-called Gulf surge. And the net result of this is we can get large organized convective systems called mesoscale convective systems, which occupy very large areas, have very highly organized structures, with large leading lines of convection and strong outflow boundaries. So we used a methodological approach to the severe weather event projection problem using a regional climate model. So the strategy is to select global climate change projection models and retrospective atmospheric reanalysis products. So these are essentially the gridded weather observations over the last several decades. These have relatively coarse spatial resolution on the order of 1 to 2.5 degrees. Then we employ a regional climate model in the second step to generate baseline long-term regional climate model simulations for historical and future periods using a grid spacing on the order of 35 to 50 kilometers. Then from using these databases of simulations of continuous simulations that span decades at a time, we can identify the individual severe weather event days in the simulation based on atmospheric thermodynamic criteria, so days with favorable atmospheric instability and moisture. Then we just simulate those days using a high-resolution numerical weather prediction type simulation at the convective permitting resolution of 2.5 kilometers. And you can see an illustration of the results from these models in terms of the radar-generated model reflectivity of organized convective structures in Arizona. And you see very clear leading lines of intense convection, followed by large areas of relatively steady rainfall. So here is some data results from all of the different modeling paradigms that we use versus the observations, which are shown in the upper left, the so-called stage 4 product. And all of these different acronyms just represent all of the different modeling paradigms. I'll explain them briefly. WRF refers to the regional atmospheric model that we used, the tool that we use at convective permitting grid spacing. This is the Weather Research and Forecasting Model. It's a model developed at the National Center for Atmospheric Research and widely used in atmospheric modeling applications throughout the United States and the world. The NCEP reanalysis at the lower left is just a retrospective atmospheric reanalysis product, and then all of the modeling paradigms at the right are just the global climate change projection models used from the Intergovernmental Panel on Climate Change Assessment. So these are the coupled model intercomparison project models, or CMIT models, and we took models representing the third and fifth generation of CMIT experiments, and you just see the various models we use. The German models, ECM5 and ECM6, and then the British models had CM3 and had GEM2. And we use the business as usual scenarios for the climate change projection, as this is the most likely to occur. And you can see that for all of these various paradigms, we get a reasonable spatial representation of monsoon precipitation of the severe weather event days compared to the observed precipitation of the stage 4 product. And we also improved the timing of the peak convective rainfall very well with the high resolution model. So it really makes the difference between we're getting a reasonable organization and propagation of convection off the terrain into the lowland region versus the observations, whether, as in the coarser resolution model, the convection is just all occurring at the same time and very little, if any, propagation. So how has atmospheric thermodynamic conditions in the Southwest changed over the last 30 years? And you see the figure on the left just shows the changes in atmospheric instability or convective available potential energy on the top, and then the corresponding changes in atmospheric moisture or precipitable water on the bottom. And from these illustrations, you see that we found there were long-term model increases in atmospheric instability and atmospheric moisture. We also found that these were quite consistent with the actual radiosonde data or weather balloon data taken at the sites you see in the dots on the figure. And in previous literature has attributed these types of changes explicitly to anthropogenic climate change. So in terms of changing atmospheric dynamic conditions, we found that the subtropical ridge of high pressure, or monsoon ridge, which is critical for the climatological evolution of the monsoon, this ridge has expanded. And so those upper level disturbances that I referenced earlier, transient inverted troughs, have now been displaced further south to the southwest U.S. on average. This contributes to less frequency of organized convective events in Arizona, but when they do occur, they're more intense because they grow more intense in a more favorable thermodynamic environment, as I just described. When we look at the actual distribution of extreme daily precipitation and how it is changing over time, and this is just an illustration for Phoenix, Arizona, which is PHX in the figure, we find in both the observed and modeled probability distributions that the distribution of extreme precipitation is becoming broader and flatter. So more extreme events are occurring in the present day, that being defined as the last 20 years versus the period 1950 to 1971. And we found very similar results in the modeled data, although albeit there's a dry bias in the model simulation. So then when we look at significant changes in extreme precipitation that were modeled and then compare those to what a gridded product that is derived from ground-based station observations, we see changes in extreme precipitation, first focusing on the station observations, more preferentially occurring in western to southwestern part of Arizona. And when we look at the changes in the model changes from the convective permitting model, the model is keying in on exactly these same types of locations. So it is more the western and southwestern part of Arizona where extreme precipitation is most significantly increasing. And this is the very location that precipitation is more subject to these larger organized convective systems that I illustrated in the Banner monsoon type precipitation days I discussed earlier. And because we're dealing with a full physics model simulation, we can also extract whatever model variables are recorded that we want. So we can also look at changes in extreme downdraft wind speed. So you recall this is related to the strength of the outflow boundaries from these strong organized convective events that would kick up the dust storms I showed in the video. And we also found the extreme downdraft wind speed potential has also increased, largely coincident in those same areas downwind of the significant terrain in the southwest part of Arizona. Now, when we repeated the same methodological approach looking in the future, in the next 20 years or so, in those CMIT models I described before, we see largely the same kinds of changes as we modeled we modeled from the observational record, from the downscaled reanalysis, and observed in the actual gauge precipitation data, just continuing forward in time. So if you focus if you focus on the mean trend in precipitation, that actually decreases, but the extreme precipitation increases, and it also increases, especially in southwestern part of Arizona, very consistent with what we saw in or what we have seen in the observed historical record and that we modeled with the model results I showed previously. So the climate change projections are really just confirming what is already happening or what has been happening over the past 50 to 60 years in the evolution of the climatology of the monsoon in the Southwest. And we can express these changes in precipitation and duration at the facility scale And here's just an example at the Berry Goldwater range. So these plots show the duration of the precipitation event in hours relative to the intensity of the rain rate. And the bottom line message here is that the greatest increases in precipitation intensity tend to be focused toward the shorter duration, high intensity events, looking at the historical record and then continuing those projections forward in time. So you see above the 20 to 40 millimeter threshold at time scales less than 10 hours is where we're tending to get more of the significant increases in precipitation. So some relevance to DoD decision making. This certainly informs future operational capability of DoD installations that were in the study area. For example, the Berry Goldwater Range in relation to weather watch and warning criteria that are presently used by the Operational Weather Squadron. And then we've investigated changes over time in model simulation results that would be impossible to observationally measure, but extremely important for DoD decision making. So I've given examples of downdraft wind speed and turbulence is another parameter. And most important, the methodological approach to modeling changing severe weather extremes, which is potentially transferable to the other areas of the United States and the world. And DoD has expressed keen interest in this latter point. And I would like to also note, if anyone is interested in these data, we're making them available to our DoD partners, the full model fields through a cloud storage interface. And because of the significance of the work, it's attracted major news headlines, and I show you examples in Climate Central, and it made the front page of the Arizona Daily Republic just this past summer. So some concluding points. There's been a long-term increase in atmospheric moisture and instability in the Southwest in recent decades due to anthropogenic climate change. A more favorable thermodynamic environment is causing our thunderstorms to become more extreme, although they're less frequent. And then high-resolution atmospheric modeling is able to pinpoint Southwest Arizona as a local hotspot where monsoon storms are now more intense, and this trend is projected to continue. And the model information generated by this work is informative for decision-making at the facility scale, and it conforms to weather watch and warning criteria. And with that, I will conclude.
Thank you so much, Chris. We have a number of questions for you. How do you know that the changes you describe in the historical period are likely due to anthropogenic climate change and not natural climate variability?
And that's an excellent question. And we selected the periods of analysis as two 20-year periods. We defined the present day as 1990 to 2010, and we defined the past period. We compare that to 1950 to 1970. And the demarcation point of about 1980 is when we know from the IPCC climate change attribution type experiments that the anthropogenic signal in the global climate system becomes statistically realizable. So if we run climate model simulations with and without anthropogenic forcing, this is when those ensembles of model simulations incorporating the human factors start to diverge from those models not incorporating the human factors, but just the natural climate variability. Those trends start to diverge in a statistically significant way about 1980 or so. And I would add that when we continued on and looked at the climate change projections in the future, downscaling a variety of global climate change projection models, the results were very similar, even in terms of keying in on the same geographic spot. And this is largely confirms that the majority of these changes, when we look at the changing intensity of extreme precipitation, it is driven by the long-term thermodynamic changes over time, so increases in atmospheric water vapor and instability.
Thank you, Chris. And we have a question from Pacific Northwest National Lab on slides on this slide. And the question is, how do you define extreme trends?
So I didn't describe the technical process of how we define extremes, but it is very important. So we use extreme value statistics. So we use a peak over a threshold technique, and we define that we look at changes in the top, basically 10% of the distribution over time, and then we assess those changes with statistical significance. And so what you see, these plots, whether it's the downdraft wind speed that you're seeing now or the changes in extreme precipitation, they're derived from an extreme value statistical theory that specifically considers the tails of the distribution and those significant changes over time.
Great, thank you. One question related to extreme weather events, specifically during the monsoon. What about the possible increase in intensity of heat waves in the Southwest, independent of monsoon? Can you elaborate or share some work that is being done in this area?
Sure, and that wasn't specifically what was done in the context of this project, but the question is highly relevant because preceding the monsoon, that we have what's called our pre-monsoon period here in the Southwest. So this is where that monsoon ridge is sitting directly over us, and when we're subject to the occurrence of the hottest and driest conditions in Arizona. Because that ridge, as I alluded to in my presentation, is becoming more intense, the heat waves associated with it, when it is centered right over the Southwest, that heat is more extreme as well. And just as a sort of anecdotal illustration, we went from our hottest June in Tucson to our wettest July. And here in Tucson, we experienced temperatures upwards of 117 degrees, near all-time record highs in the month of June prior to the onset of the monsoon.
Thank you, Chris. And since you're an official member of the Hydrogeology Department, can you tell us whether your data can also be used to inform projection of hydrologic extremes like flash flooding?
That's an excellent question, and I'm glad it's asked, and the answer is absolutely yes. And we certainly want to pursue this as the next phase of research. And these data there that have been generated as part of this project can serve as a database that we could force very high-resolution hydrologic models in a one-way forcing type mode to look at issues of flash flood estimation and changes in characteristics of flash floods over time. And we are actively working with collaborators at the National Center for Atmospheric Research, specifically in the Research Applications Laboratory, in the development of the WRF hydro model. So this is the hydrologic component of the WRF model. That's the basis of the National Water Model. So we are working on it, and we just, in fact, got a funded NOAA proposal to do exactly that. But if anyone on the call is interested in working with us on that, please, we know this is a very urgent issue, and we want to move to it as soon as we can.
Great, thank you, Chris. And I'd like to broaden the discussion a little bit and try and get some broader questions out there for you and Dave. So let's start with Dave. Dave, given that monsoon patterns are changing, how do you think this will affect ecosystems of interest to DoD installation managers?
I see Chris's work here as hugely relevant to the management of aquatic ecosystems, because we know it's not just the, I talked a lot about how the hydro period was important, whether you're intermittent or perennial, but it also turns out that the timing and intensity of events strongly affects certain species and certain communities and can actually change the community composition within a stream network. Not only that, my research group has shown as part of another project that the invertebrate species themselves can evolve in response to the frequency and intensity of monsoon thunderstorms. So we're talking about ecological changes occurring as a result of these changes in monsoon and storm patterns, and also the organisms evolving in different directions. So that's wide open.
Thank you. Chris, would you like to add anything?
I guess I would say it's important to consider the cascading effects of how a changing climate is interacting with ecosystems. So a good example that comes to mind related to what I just said of this year's climate here in Tucson is during that hottest June that we also had a major forest fire that occurred in the Catalina Mountains, just to the northeast of the city. So for increasing incidence of forest fire, then couple that with perhaps more intense monsoon precipitation, that is putting increasing stress on ecosystems, because you're rapidly changing from one climate extreme to another, even within the course of several weeks.
Thank you, Chris. And Dave, although the variability in monsoon rainfall and stream flow patterns is important to desert environments, to what extent do you think your work applies to regions with higher annual rainfall?
Right. So we've developed a lot of our models and a lot of our thinking looking primarily at these networks of desert ecosystems, which include perennial sites that behave to a large degree like a more mesic site would in a wetter climate or a more northern climate. But one thing that is clear is that streams function as networks. So even in more mesic environments, perhaps in the northeastern United States, in the central Great Plains of the United States and elsewhere around the world, there's still a high degree of variability in stream hydrology. So I think the general lessons still apply, that you have different types of hydrologies harboring different components of the aquatic biodiversity, and that they need to be managed as networks of sites with different properties rather than as just single sites that have certain desirable characteristics. So I think that ecology is quite transferable to other types of climates with different rainfall patterns.
Thank you. And Chris, what would be your overall recommendation to DoD as to an effective strategic approach to climate change projection that is meaningful at the facility scale or at the installation scale?
Yes, I think one of the loud and clear messages that came from our project is that model resolution and physical process representation of extreme weather really matters. So the use of the so-called convective permitting scale appears to be really critically important, and obviously it can get down to the scale of of kilometers that is more matching the actual DoD facility scale. But more important, it's getting the physical process representation right in a much more what I call physically confident way. So in Arizona, it really makes a difference between whether we're representing reasonably organized severe convective events, so mesoscale convective systems, versus we don't. And if we don't represent them, we can be on facilities like the Berry Goldwater Range or Yuma Proving Ground, and we can be depending on coarser resolution climate change projections. And those models are giving physically an incorrect answer. So I think convective permitting modeling, it takes a lot of computational resources and human resources to do this type of work. But if it really means getting answers that we have the physical confidence in, I strongly believe it's worth the effort.
Thank you, Chris. And Dave, do you have any overall recommendations on your end?
Well, I think that, you know, what Chris and I have both shown is that the baseline of climate is shifting. I mean, we're entering a zone of non-stationary dynamics where weather patterns are changing, and the dynamics of individual thunderstorms and the general patterns of rainfall are going to be shifting, and that we have to take a broader view that incorporates that variability. I think also on the ground, from the point of view of what I talked about with managing species, if we embrace this spatiotemporal variability on the ground and include that in the way that we monitor, you know, our ecosystems of interest, if you start with that, it's going to be much easier to incorporate climate variability and change through time into that methodology than if you ignore it. So I think that's where the things that Chris has been talking about and the things that I was talking about really go together.
Well, I'd like to thank both of you, Dave and Chris, for a fascinating webinar. In fact, thank our listeners for hanging in there. I'd like to remind you also that our next webinar is on Thursday, October 19, and it will focus on SERDP and ESTCP research efforts on laser depaint and surface preparation mechanisms and technologies. This webinar will feature two speakers, Mr. Tom Nagai of the Air Force Materiel Command, who will discuss the use of laser technology for aerospace maintenance. And then we're going to have Dr. Adrian Sabu of the Oak Ridge National Lab, who will talk about a novel non-chemical process for surface preparation using laser technology. Registration is already open for this webinar, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentations from today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a quick moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you for your time.